This is Chapter 5, Part 1. This section is going to be all about chemical reactions. So we start with the learning objectives. So you see by the end of this presentation and your practice, you should be able to balance chemical equations. You should be able to classify the following equations. We have synthesis, decomposition, single and double replacement, combustion, and oxidation reduction reactions. So you should be able to recognize each of those. And then lastly, you should be able to determine what reactant is being oxidized and reduced in a redox reaction and what substance is the oxidizing agent and which is the reducing agent. So by the time you finish week 7, these should be what you can check off. Alright, so let's start with chemical equations. And so it says that a chemical equation uses chemical formulas, which we learned how to write in the last chapter, and other symbols showing what reactants are the starting materials in the reaction and what products are formed. And so when we write a chemical reaction, the reactants are always written on the left of the yield sign, and the products are always written on the right-hand side. And we use something called coefficients. These are the big numbers in front to show the number of molecules of a given element or compound. And so the example that you see here, the reactants have been labeled for you. They're to the left of the yield sign. Remember, this is the yield sign. Separates the reactants from the products. And the products are on the right-hand side of the yield sign, and then it points out coefficients. And so we use coefficients to balance the chemical equation. So the way you would read this equation, you would say 1 molecule of methane plus 2 molecules of oxygen gas produces 1 molecule of carbon dioxide plus 2 molecules of water. And this would be a balanced equation. So we have to look at something called the law of conservation of mass. This is kind of the bedrock of chemistry. Law of conservation of mass states that atoms cannot be created or destroyed. And so that's why we have to balance equations. So we use coefficients to balance a chemical equation. A balanced chemical equation has the same number of atoms on each side of the yield sign. And that's how we would know that the reaction is balanced. So there give you some examples here. Same number of atoms. So according to the law, we have to have the mass has to be the same. The reactant's mass and the product mass has to be the same. So we can equate that to number of atoms because each element has a specific mass. And if the atoms are the same on both sides, therefore the masses would be the same. So you see a breakdown here of this simple equation where we have 1 carbon atom, 4 hydrogen atoms, and 4 oxygen atoms. These are all of our reactants. And on the product side, we have the same number of each of the atoms. And so we say that this equation is balanced. If we were to total the masses on both sides, the masses would be equal, and that's exactly what this law of conservation of mass requires. There are some symbols that we use an awful lot in equations, and you need to be familiar with what these symbols are and what they mean. And so the arrow means yields. Some other words that you could use are produces or makes. Then we have this, looks like a triangle. This is actually the Greek letter delta, and oftentimes in chemistry, delta refers to a change. When it is written with an equation, it refers to heat, so a change in the heat. The lowercase s in parentheses refers to the fact that the compound that it is describing is a solid. The L stands for liquid. The G stands for gas. And then lastly, AQ stands for aqueous, which means dissolved in water. And so these last four symbols are talking about the state of matter of a particular substance. And so when you see these written in a chemical equation, you should be able to interpret them. All right, so let's go to how to balance an equation. So here's the example given to us. It says write a balanced chemical equation for the reaction of propane, gives us the formula, with oxygen gas to form carbon dioxide and water. So the first thing you want to do is write the equation with the correct formulas. So you have to start by writing correct formulas. And in this case, they gave me all of the correct formulas, so I'm simply going to copy them down. So C3H8 plus O2. When it says to form, I'm going to put the arrow, carbon dioxide, CO2. When it uses the word and, you put a plus sign, water. So it makes a note here saying that the subscripts in a formula can never be changed to balance an equation, because changing the subscript changes the identity of the compound. So oftentimes I think about these formulas that I write. Once the charges are balanced, I kind of put them in a box, either literally or just in my head, because you cannot change anything inside the box. So in order to balance the equation, you have to add a coefficient, and that coefficient changes all of the elements in that compound. So just note that you can't change any of the subscripts. The subscripts are the small numbers at the bottom, so those cannot be changed once the equation has been written correctly. All right, so then step 2, once you have the equation written, step 2 says balance the equation with coefficients, and you're going to do this one at a time until the equation is balanced. So if we go back to what we wrote up here, we can make what I like to call maybe an inventory of our different elements involved. And so right under the yield sign, I would make a list of all the different elements. And so I can see that we have carbon, we have hydrogen, and we have oxygen. We have that on both sides of the yield sign. And so then I make an inventory or a count of how many atoms of each that I have. And so I see that there's first C has a subscript of 3, so that means there are 3 C's. There are 8 H's. There are 2 oxygen. That's all on the reactant side. On the product side, I see there's 1 C, there's 2 H's. Now this is a little tricky. You can see that there are 2 oxygens here, and there's 1 oxygen here, and there's a plus sign in between. So you have to add that together. 2 plus 1 is 3. And so by making this inventory, we can clearly see that the number of atoms on each side is not balanced, and therefore we want to add coefficients in a way to make both sides have the same number of atoms. So on step 2, it says that we must add coefficients. Now remember, the coefficient has to go in front of the compound, and it affects the entire compound. And so this suggests that you should balance your carbons first. And so on the reactant side, we had 3 carbons. On the product side, we just had 1. So we put a coefficient of 3 in front of the CO2. And by doing that, it makes 3 carbon. It also changes the oxygen to 3 times 2, which is 6, plus 1 more over here, so a total of 7. Okay, and the next step, it says to balance the hydrogens. And so on the reactant side, we have 8 hydrogens. We need to put a coefficient in front of the product. That one multiplied by 2 would give me 8. So they chose the coefficient of 4. 4 times 2 is 8. And so in this way, we have both the carbon balanced and the hydrogen is balanced. All right, finally, we need to balance the oxygens. And so if I were to count how many oxygen I have on the product side, we have this 3 times 2. 3 times 2 is 6. And then there's the plus sign. And then I have 4 times just 1 oxygen, which equals 4. So 6 plus 4 equals 10 oxygen on the product side. So I go to the reactant side and I think what times 2 will give me 10, and of course that is a 5. So this is the final balanced equation. C3H8 plus 5O2 yields 3 carbon dioxide plus 4H2O. Let's just go through and count and make sure that it's a balanced equation. It's a good idea to take the time to do that. So we see on this side we have 3 carbon, and here's 3 carbon. So carbons are balanced. I have 8 hydrogen. 4 times 2 is 8 hydrogen. So the hydrogens are balanced. Here I have 5 times 2 is 10 oxygen. Here I have 3 times 2, that's 6, plus 4 equals 10. So on both sides of the equation, both sides of the yield sign, I have an equal number of atoms, and therefore the reaction is balanced. Step 3, lastly, says check to make sure that the smallest set of whole numbers are used. And so once you have balanced equation, you want to check your coefficients. Remember, the coefficients are in front of the molecules, and you want to make sure they're in their simplest form. And so here I have an understood 1, a coefficient of 1, a 5, a 3, and a 4. And there's no way to simplify those numbers. So this would be the smallest set of whole numbers. So we can say check. Those are done. So you'll have lots of practice balancing equations, and you want to continue that practice until you can do it fairly quickly. Balancing equations is an important skill, so make sure you can master that. All right, the next topic is about types of reactions. So the majority of the chemical reactions that we'll be talking about fall into these 6 categories that were mentioned earlier. So let's write them down again. We have synthesis reactions, and I believe your textbook calls them combination reactions. Those are the same thing. Secondly, we have decomposition. Next is single replacement. Then we have double replacement. Next we have oxidation reduction. Reactions. These are often called redox for short. And then lastly we have acid-base reactions. And so the acid-base reactions, we'll talk more about that in chapter 9. So we'll save that for a little bit later on. So let's just jump into these 5 types and look a little closer at what is happening here. So the first one that we had was synthesis. Let me change colors. Synthesis reaction. Remember, also known as combination reaction. So it says it's simply the joining of 2 or more reactants to form a single product. So underline the word single product. this is the clue that you have that this is a synthesis reaction. You're going to have two or more reactants. These reactants could be elements, they could be compounds, but you will always only get one product. So here they have the simple pattern here, A plus B produces a new compound that we'll call AB. So this is a nice pattern to memorize. Next we have decomposition reactions. And just like the word says, you see the word decompose, which you know means to break down. That's exactly what is happening here. We have a single reactant, underline that part, single reactant breaks down into two or more products. And so we see the pattern here that they have written for you. We'll call that our compound AB would break down into its individual parts. So A plus B. And they've given you a particle representation of what that might look like. All right, the next one is the single replacement. It says it's a reaction in which one element replaces another to form a new compound. So every time you're going to have a single element, that would be the A, single element, trying to replace something in the compound. And so in this example, A was able to replace B in the compound. And so you have A plus BC, and so B is going to be by himself now, and now we have a new compound with A and C. So this would be a great pattern to memorize for single replacement reactions. The double replacement reactions, and just like the name suggests, you have two compounds that are trying to change places. And so the pattern that you see here, AB plus CD, these are our two compounds. And the A and the C, the two cations in these ionic equations, are simply going to change partners. So instead of A being paired with B, now A is going to be paired with D. And then we have C paired with B. So here is the pattern for a double replacement reaction. Here are some examples that you see. Oftentimes students confuse single replacement with double replacement. And so here are a couple of real examples to take note of. One thing to recognize in a single replacement reaction, you should always pay attention to what type of element the single element is. In this case, you have Br2 as your single element, and if you look at the periodic table, you'll see that that is a nonmetal, and so it is going to try to take the place of the nonmetal in the compound. And so you can see it has accomplished that. Instead of NaCl, we have NaBr, and then Cl is left by itself. Remember, don't forget about the diatomic molecules. Diatomic molecules always exist in pairs, and so Br2 and Cl2 are examples of those diatomic molecules. And you have to be sure and put the small 2 following each of the diatomic molecules. Now when these diatomic molecules are in a compound, then it's just a matter of balancing charges. They're not diatomic when they're in a compound. The second example, you see a single element is a metal, and so it would replace the metal in the compound. So iron is trying to replace copper, and so instead of copper sulfate, we end up with iron sulfate. So for single replacement, you're looking for the single element in the reactant side to know how to proceed. And then in the double replacement, both ionic compounds would trade their partners. All right, let's move on then to oxidation reduction reactions. And so the word oxidation is a label put on an atom that loses electrons. And so an acronym that I use in my class is OIL. Oil, oxidation is losing electrons, and then reduction is gaining electrons, and so that would be RIG, oil rig. Helps me remember which one's losing and which one's gaining. And so oxidation is losing electrons and reduction is gaining electrons. So both of these processes always occur together in a single reaction, and this type of reaction is called oxidation reduction reaction, or simply just a redox reaction. So you'll hear me refer to this as redox reactions, just as a little shortcut. A redox reaction always has two components, one that is oxidized, losing electrons, and the other that is reduced, gaining the electron that was lost. A redox reaction involves the transfer of electrons from one element to another. So let's take a look at what that might look like. Here we have a single replacement reaction. A zinc metal plus a copper 2 ion is going to produce a zinc 2 ion and copper metal. And so each of these processes that we see highlighted here can be written as an individual half reaction. So we're going to write the oxidation half reaction first. And remember, oxidation is oil. Oxidation is losing electrons. And so we see here that zinc metal went from a charge of 0 to a charge of +2. And so that +2 is a result of losing 2 electrons. So we have our half reaction written. Zinc metal goes to zinc 2 plus, and then we put plus the 2 electrons that were lost. So this is what's called a oxidation half reaction. And then we also have the reduction half reaction. So the other half of the equation is going to show us where those electrons went. And so the copper 2 ion went from a +2 charge to a 0 charge. And so copper 2 gained 2 electrons to become copper metal. And so we have our reduction half reaction, as you see here. Copper 2 ion plus the 2 electrons produces the copper metal. So just some general features of a redox reaction. A compound that is oxidized. Remember, oxidized means losing electrons, while causing another compound to be reduced is called the reducing agent. It caused reduction to happen. So the compound that was oxidized, which was zinc, caused copper to be reduced. Therefore, it is called the reducing agent. These terms can be a little bit confusing. On the other hand, a compound that is reduced, we see that the copper 2 ion was reduced. RIG, rig, reduces gaining. So it went from +2 to a 0 charge. And so a compound that is reduced while causing another compound to be oxidized is called the oxidizing agent. Copper 2 acts as the oxidizing agent because it causes oxidation to happen. It caused zinc to lose electrons and become oxidized. So here are some other examples of oxidation reduction reactions. Notice when the electron is written on the product side, these are written in terms of the electrons being lost, and so all of these are oxidation reactions. Remember, oil oxidation is losing, and so this is showing how many electrons were lost. And then on the other side, remember, Rig reduction is gaining electrons, and so this is showing the electrons that were gained by the particular substance. Some real-world examples of oxidation reduction reactions happening would be the formation of rust. And so in this picture, it's kind of small, but you see that we have some metal, maybe some metal fencing or something, and over time that metal fencing will develop a brownish color, and we call that rust. Rust is actually a chemical compound. Fe2O3 is the formula for rust. And so when we break down this reaction, we see that iron in the reactant side, a solid piece of iron, has a charge of 0. And then in the product side, iron has been oxidized because it lost electrons and turned into iron with a 3+ charge. So remember, the charges tell you whether they're positive or negative, tell you how many electrons were either gained or lost. So when we have an ion is simply an atom with a charge. And so a plus charge means that the atom has lost electrons. Electrons have a negative charge. So think about having a negative attitude, maybe. If you lose your negative attitude, you're going to become more positive. So maybe that'll help you remember that when atoms lose electrons, they take on a positive charge. And a negative charge for an ion means that it has gained electrons. Electrons were gained. So it's a little counterintuitive, but if you can keep in mind that electrons have a negative charge, that will help you understand the signs. And so here, iron going from iron metal to an iron ion, that's a loss of electrons. And then here we have oxygen going from a 0 charge to a -2 charge. This -2 indicates the gaining of electrons, and so oxygen is reduced when iron is produced. Some other examples of redox reactions have to do with batteries. So anytime you see a battery, inside that battery there is a redox reaction taking place. And so here is a typical flashlight battery. Looks like a C battery. You see that inside the battery you have zinc oxide, and manganese oxide. And so those two chemicals go through a redox reaction, and electrons are transferred from one atom to another. One is oxidized, the other is reduced, and so that is a flow of electrons. And anytime you have a flow of electrons, you have electricity. And so when you turn the flashlight on, that starts the reaction, that starts the flow of electrons, and we can harness that and turn it into, in this case, light energy. And so that's a little bit about how batteries work. It all has to do with chemistry. All right, let's recap what we've learned here. So oxidation results in the gain. of oxygen atoms. So another way to, instead of just looking at charges, some reactions are a little bit harder to determine what's being oxidized and what's being reduced. And so this will help you with those types of reactions. So it says oxidation results in the gain of oxygen atoms and the loss of hydrogen atoms. And then reduction would be the opposite, loss of oxygen atoms and the gain of hydrogen atoms. So instead of looking at changes in the charges, you see we have a combustion reaction. And so in this type of reaction, it's just easier to focus on the gain and loss of oxygen and hydrogen atoms. And so we see that CH4 turned into CO2. So we know that CH4 was oxidized because we had a loss of the hydrogen atom. The 4 hydrogen atoms were lost. And then oxygen is reduced because it went from O2 to H2O. So we gained hydrogen atoms here. So we lost hydrogen atoms here and we gained on this side. So this is also a type of redox reaction. So this one is a little bit more challenging to see, but if you can just keep in mind that you can look at oxygen and hydrogen atoms, it's helpful to make note of that. So another example of redox reactions, again this is a battery, but this is a battery that sometimes is inserted as a pacemaker. So you may have heard of a pacemaker being implanted in a patient that is having trouble, maybe their heart does not beat on its own as well, and so this is an electrical device that can send an electric shock to the heart and trigger the heart to beat. And so just like with any battery, the thing that is creating the electricity is a redox reaction. And so in this case we see lithium and iodine are the chemicals inside the battery. And so as the lithium atom is oxidized and the iodine atom is reduced, we have this flow of electrons, and that is what powers the battery, and the battery is what triggers the heart to beat. So this is very important in the healthcare industry as well. All right, this concludes part 1 notes, and so we will stop the video here.